Hey everyone, and welcome. For more than 100 years, Albert Einstein's ideas have been the absolute foundation of physics. But what if the ultimate test for his theories is hiding in the darkest, most extreme places in the entire universe? That's what we're diving into today, how the very first images of black holes are being used to poke and prod the fabric of space-time itself, to see if Einstein really did have all the answers. Okay, this quote right here, this basically sets up our entire cosmic detective story. What it's saying is that, yeah, the evidence we have seems to back Einstein up. But, and this is a huge but, there's just enough wiggle room, just a little shadow of a doubt, that could literally change everything we think we know about gravity.
So let's start with the basics. When we see one of these incredible pictures of a black hole, what are we actually looking at?
These images are so much more than just a snapshot. You can think of them as a cosmic fingerprint. A black hole is so incredibly massive that it literally warps space and time around it. That shadow we see, that's the silhouette it casts on the superheated glowing gas that's swirling just behind it. It's a fingerprint left behind by gravity itself. All right, now let's bring in our prime suspect, Albert Einstein's theory of general relativity. What does it have to say about this fingerprint? For well over a century, general relativity has been the undisputed champion. It's predicted everything from gravitational waves to the way starlight bends, and every single time it's been spot on. It's our standard model for how gravity works on the biggest scales imaginable.
So according to general relativity, a spinning black hole should be what's called a Kerr black hole. And what's just amazing about this is that this incredibly complex, universe-bending object can be described by just two numbers, its mass and its spin. That's it. This beautiful simplicity is why it's been the gold standard for astronomers for decades.
And this is where the real test comes in. The Kerr model makes a very specific testable prediction. A black hole with a certain mass and a certain spin should cast a shadow of a very specific size. If the shadow we measure out in space matches that prediction, well, that's another huge win for Einstein.
But, physics is never quite that simple, is it? What happens when the world of the very, very big, general relativity, collides with the bizarre world of the very, very small?
This right here, this is the central crisis in all of modern physics. On one side, you've got general relativity, our perfect rulebook for stars and galaxies. On the other, you've got quantum mechanics, the rulebook for atoms and particles. The problem? The two rulebooks completely contradict each other. And a black hole is the one place in the universe where both sets of rules have to apply, and they just break. And this conflict has kicked off one of the greatest quests in the history of science, the search for a unified theory of quantum gravity, a single theory of everything that can explain the entire universe from a tiny quark all the way up to a giant quasar.
So to test these new ideas, scientists have come up with a clever trick. They add what they call quantum corrections to Einstein's equations. You can think of it like a single knob, let's call it alpha. If you set that alpha knob to 0, you get a perfect, standard, Einstein-style black hole. But if quantum gravity is real, turning that knob even just a little bit should start to change things.
So this is the million-dollar question, right? What happens to that cosmic fingerprint, that shadow, when we start turning that quantum alpha knob? If these quantum effects are real, they should actually change the shape of space-time, which in turn ought to change the size of the shadow. And here is the fascinating prediction from these alternative theories. According to the models, turning up that quantum correction knob actually causes the black hole's shadow to shrink. So now we have a clear, testable difference. Einstein predicts a bigger shadow, and the quantum challengers predict a smaller one.
So we have two competing predictions. It's time to bring in the evidence, gathered by a telescope the size of our entire planet, the incredible Event Horizon Telescope. First up, the supermassive black hole at the heart of galaxy M87. The EHT measured its shadow at 37.8 microarc seconds. Now, to give you an idea of how insanely small that is, it's like trying to measure a donut sitting on the surface of the moon. It's an incredible measurement. But look closely at that plus or minus 2.7. That little bit of uncertainty, that's the key to this whole story. And next up, the beast in our own backyard, Sagittarius A star.
Its shadow measures 48.7 micro-arcseconds. It looks bigger just because it's so much closer to us. But notice the uncertainty is also way bigger, plus or minus 7. That even wider margin of error makes it even trickier to tell the competing theories apart.
So we have the predictions from the theorists, and we have the measurements from the astronomers. What did the cosmic jury decide?
So who's right? Does the data we have point to the larger shadow that Einstein's theory predicts? Or does it favor the smaller shadow from these new quantum gravity ideas?
And the verdict is a cliffhanger. It's incredible. Because of those uncertainty ranges we just talked about, the measured sizes for both black holes fit perfectly with Einstein's prediction, but they also fit with a whole range of the quantum-corrected models that predict a slightly smaller shadow. So for now, both sides can look at the data and say, see, we were right.
So where does that leave us?
Well, this isn't the end of the road. In fact, it's the very beginning of an entirely new way of doing physics.
The big takeaway for right now is that Einstein's century-old theory is still undefeated, even when we test it at the most extreme place we can possibly imagine. The very edge of a black hole, his predictions hold up. It's just a stunning, stunning testament to his genius.
But that little window of uncertainty, that tiny gap where new physics might be hiding, that is the most exciting place in all of science right now. It's like a crack in the door, and physicists are doing everything they can to kick it open and see what lies beyond.
Future telescopes are going to shrink those error bars, giving us a much sharper view of these cosmic shadows. And as they do, we're left with this one absolutely thrilling question. The next time we get a picture, will we just see a clearer version of Einstein's universe? Or will we finally see the first faint hint of a whole new law of physics waiting for us in the dark? We'll have to wait and see.